again, from a terminology perspective, I want to be able to say integrand and have you guys be like, oh yeah, that's what that is, as opposed to what? Okay, so here we go. The tall, skinny S.
Integral.
That's an integral symbol. That's what we typically call it. Tall, skinny S means integral. What about the expression inside? Like in this case, it's f of x. That's the integrand. That's right. Integrand. That's the thing you're finding the antiderivative or the integral of. What about the dx? That's the differential. That's what we kind of finished that last chapter 3.9 with. That is the differential. So I'll just put diff for differential. All right, and then what about the thing right there on the right side that's represented with the capital letter F? It's the antiderivative, yep. And then the plus C is called what? Constant of integration. And at the start of the video, did you learn a little bit about why that's there? Remember at the start, it could have been, I can't remember if it was like x cubed. Was that my, or no, it was x to the fourth. So it could be like an antiderivative could have been x to the fourth plus 10, x to the fourth minus 1,000, x to the fourth plus or minus any constant would have worked for an antiderivative. And so we wrap all those up into just a simple plus c. It could be anything. Later on, we'll be given information where we could actually figure out what that plus c is. Later on today, actually. But for now, we just say, okay, there's plus some unknown constant. Okay. So then what followed after that, of course, was this little list of rules. As you can tell, I have unceremoniously just simply copied this right out of your book. I didn't feel any need to just rewrite something that's been written well. You got the left side, you got all those derivative rules, and the right side, you have kind of the corresponding integral rule. As far as which ones are commonly used, I mean, they'll certainly all be used. This one right here, the power rule for integrals, will be used repeatedly over and over and over. Although not everything is a power rule, it will be used a lot, definitely. And then all of your trig stuff down here, that'll be used very, very frequently as well. And we're certainly, I would say, certainly leaning on you guys remembering what the derivative of secant is, or the derivative of cosecant is, so that you can recognize the reversing of that. Does that make sense? So, hoping that you've done that. And the rest of these rules at the top, I mean, the sum and difference rule, constant multiple rule, all those will be used repeatedly. But I thought I'd emphasize that power rule there. And then, of course, in the midst of the video, you got an opportunity to practice several of these using those rules. 5 of them, 6, 7, 8 of them. Wow, that's a lot of practice. Hope that made sense in the video. You guys feeling okay? All right. Well, I would like to, I would just sort of like to test you out a little bit. See what you can do here. See how much you remembered. And we'll go over these in detail, talk them over. So if you guys could try numbers 9, 10, and 11. You should see that these somewhat go with the video and definitely go with those rules. Work together, try it out. We'll go over the details here. I'll be happy to answer questions from you once we get these done. So for number 9, as you think this through, you want to identify what rule is what. So for instance, if you looked at number 9, and maybe you didn't do it this way. I hope that you didn't do it this way. But if you did look at number 9 and you said, hey, look, why don't I just add 1 to the exponent and divide by that new exponent? In other words, maybe you used a power rule. That would definitely be a mistake. So if you wrote 4 times secant cubed of x over 3, maybe plus c or something like that, listen, that would be incorrect. It would be understandable why you would do that, but that would be incorrect simply because this is not a polynomial type power rule situation. This is an integral of a trig, an antiderivative of a trig function. And so the idea would be, my hope would be that you would look at this and maybe you'd see this. I don't know that this is a totally necessary step. Did anybody do this? Did anybody bring the 4 out? Yeah. Because you are certainly welcome to do that. I don't know that it's going to make a gigantic difference on this one from like a connection standpoint. Later on, I think that would make a big difference, and so that wouldn't be a bad thing to do. Yes?
If you bring it out, would it have to be 4x?
No.
Why not?
So with a constant multiple, so what you're getting mixed up on is you're getting mixed up between the integral of a constant versus the integral of a constant multiple. Right? So if you're doing the, and go back to the rules, look at the rule that has the k. So if you've got the integral of k f of x, it can become k times the integral of f of x. And that's what this is, because it's not a constant, it's a constant multiple.
I was right on the first time.
So,
You correct.
what I would be relying on you guys to do here is I'd be relying on you to remember that the derivative of tangent is secant squared. So the antiderivative of secant squared would have to be tangent. And so what you'd end up with here is 4 times the tangent of x plus c. A note on quizzes and tests, that plus c absolutely must be there. If it's not, you will not be getting full credit for an answer to this question. So if you just put 4 tangent of x, you'd get some credit, but not all. So make sure you have the plus c in it.
C on the answer, I'll give it to you for it. The C.
Or you're speaking for me now?
Yes.
No, I won't.
You'll
I
give
s-
us a C on the question.
Oh, you'll get a C? No, no, you'd maybe get a little better than a
I'll
C.
give it to you.
It's hard to say. That was pretty clever, though. I will give you that. And Peyton, your joke is forever immortalized here on video. Number 10.
I want to see like 80,000.
Someday you'll be famous. Yeah. Look, well, just watch for the comments on YouTube. They'll be like, at 6:15, that joke was awesome. Anyways, number 10. So number 10 is not a trig function, right? It's 7 plus x squared. So there's a number of ways you could deal with this. If you wanted to split it up, you could. If you didn't want to split it up, you really don't have to. So Peyton, to contrast the idea with the 4 and number 9 here, the 7 does not get to come out. And the reason the 7 does not get to come out is because it's not a constant multiple. It's a separate term within the integrand. So we couldn't do anything like that. But we could do this. We could say that the integral of 7, or the antiderivative of 7, is simply 7x. And then the antiderivative of x squared, this is where that power rule would come into play. You'd add 1 to the exponent, and then you divide by the new exponent. So maybe you could put plus x cubed over 3, and then, of course, plus c. Something along those lines. Of course, you could also have 7x plus 1/3 x cubed plus c, just a slightly different form there, but sometimes that's a little bit better to work with. Question?
I noticed you don't put equal signs. Are we allowed to put like equal signs between?
I'm really careful with my equal signs, simply because it's like such a powerful statement to say this thing on the left and this thing on the right have the same value. So I want to be really careful with that. I'm not going to put those in there unless I really want to have an equation. If you put equals and equals, you might find some college professors that get really offended by that
Okay.
and say, no, you should not be doing that, simply because we didn't really have an equation to start with. And I would say if you use the equal sign as a and my next step is kind of a thing, you want to be careful with that, because sometimes we make mistakes with that. Catherine, I don't think that I would take off for that. But you'd want to be really careful, because if you linked two things that are not equal and said that they are equal, now I would have a problem with that. So I would be careful with it, but really the safe way is to not put them. Or if you really want some kind of a notation, just do the arrow thing. Just say, and my next step is, and my next step is. There's really no way you could go wrong with that as far as messing up equal sign kind of things.
Okay.
Yeah, good question. Okay, and then finally number 11 was the last one in this little set. Did you all flip up the x to the 5th up to the top? You really want to do that. You're going to find that doing the integral or the antiderivative of a fraction becomes very problematic very quickly. And so you don't want to be casual with fractions. You want to turn them into something that's not a fraction if possible. So my first step would be to do that, 13 times x to the negative 5th dx. And then if you wanted to bring the 13 out, I think that would be a logical step as well. 13 times the integral of x to the negative 5th dx. And then this fits squarely within the power rule concept. And so people will mess this up though, right? We're adding 1 to the exponent. So what's negative 5 plus 1? Man, if I had $10 for every time somebody said negative 5 plus 1 was negative 6, I'd have quite a bit more money than I do right now. I don't know if I'd be rich or not, but it'd be a lot more. So you want to be careful with that. So when you add 1, you do get 13x to the negative 4th. You then divide by that new exponent. And then, of course, we have plus c hanging on the end there. So negative 13 fourths, x to the negative 4th plus c. There is no compelling reason to flip the x to the negative 4th back down. Although if you do, that's not wrong, but you can leave it as x to the negative fourth, and it's no problem. I know sometimes we're trained in our pre-calc classes and algebra 2 classes that you always have to flip negative exponents down or up or wherever they should go. Nothing wrong with that, but nothing is compelling you to do that either, at least not in this class. Okay, so how'd that go? 9, 10, and 11?
All right.
Do you have evidence that you learned something from the video? I hope that's the case. Let's keep moving. Let's see what the next little set looks like after 9, 10, and 11. What do we have here? We've got, shocking, 12 and 13. Let's try 12 and 13 together. I'll give you a couple minutes to do that. Then we'll get into our last few topics.
I had 3%. I think that's pretty fair.
Okay, let's take a look at 12 and 13. 12 and 13, I'll say this repeatedly. I want it to sink in. Number 12 is a fractional integrand, right? Fractions get really tough really fast, and so if we can do some algebra to avoid integrating a fraction, we will do that every time. Later on, it'll be unavoidable. Right now, it'll always be avoidable, okay? You'll learn a handful of techniques. You'll learn like 3 or 4 techniques on how to deal with fractions. It's not that hard, but if we can avoid it, we will. So what I'm going to do with this one is I'm going to flip that denominator up to the top. So that would give me integral of x cubed plus 7x squared minus x. And then I flip that denominator up, so it would be times x to the negative 1. You will also find out in the near future that the integral of a product, which is what that is right now, right? It's something times something. The integral of a product is similarly difficult to a quotient. And so we will avoid, as much as possible, doing the integral of a product. Again, later on it won't be avoidable or desirable, but right now it is. I'm going to use the distributive property to get rid of the fact that it's a product. So that would give me integral of x squared plus 7x minus 1 dx. So once I've done that manipulation where I've flipped up and then distributed, now I can go through and do a power rule for integrals 3 times, and I should be in good shape. This would then give me 1/3 x cubed plus 7/2 x squared minus x plus c for my final antiderivative there. Any questions? Okay, good news. That's good. So number 13 then. Number 13 is not a power rule situation. How do I know this?
It's the sine cosine.
Yeah, it's like a trig thing, right? So it's a trig thing. Yeah, that is a technical term there. Did you guys all take the 3 out? Okay, you take the 3 out because it's a constant multiple. You can do that. And then it comes down to this. What is the antiderivative of cosine? It's positive, right? Yes. So it's 3, positive 3, sine of x plus c. The sine and cosine plus minus thing just flips around for antiderivatives versus derivatives. I hope that makes sense. You guys have any questions on that one? Awesome. Good deal. So let's take a look here at our final couple of questions in our notes for this section. And here we go. So we're going to be looking at what's called initial conditions and particular solutions. So what this is supposing is this. I want you guys to get kind of a basic idea. Let's fill in the little blanks down below, and then we'll kind of build this out. So a differential equation is an equation with one or more derivative. What goes in the blank? Derivative. Okay, so how do you undo a derivative or differential? Like, what's the opposite of a derivative or a differential? Integral, yeah, an antiderivative or an integral. And this is, I want to pause on the blanks here for just a second. So when you think back to the 5 questions that we have done so far, we're finding the integral of this, the integral of that, whatever. We get the plus c on there. Aren't we kind of presupposing this? Aren't we kind of thinking that someone previously has done a derivative and gotten whatever? Like if you think about the last one, it was like 3 cosine of x. But you think of it as like somebody has previously done a derivative and they got 3 cosine of x. And what we're trying to find is what was the original function? Like, what did they do the derivative of to get this 3 cosine of x? That's kind of the essence of an antiderivative. And so you look at a question or like a statement like we see up there at the top, dy dx equals 3x squared minus 1. Somebody has done a derivative. They got dy dx equals 3x squared minus 1. And our job potentially could be to say, well, what was the equation that they did the derivative of? So like we go back a step and say, what did you have to differentiate to get this? That make sense? And so we call the answer to that question a solution, or in some cases we'll call it a particular solution if we have what's called an initial condition. So let me fill in a couple of blanks here, and then we'll go back up there to the top, and I'll give you a chance to do one of these on your own. So if an initial condition is not given, so we'll talk about what those are, show it to you here in a second. If an initial condition is not given, the answer will be what we call a general solution. And what characterizes a general solution is the plus c. So if it's blah, blah, blah plus c, that's what we call a general solution. But if an initial condition is given, the answer will be a particular solution. And with a particular solution, you will be given enough information to actually find what the c is. So instead of blah, blah, blah plus c, it'll be blah, blah, blah plus 12, or whatever the c ended up being, or minus 17, or who knows. So what I thought I would do, I want to give you a basic plot of how this works, and Colin, this might answer a little bit of your question from earlier. I want to take that dy dx equals 3x squared minus 1, and you can write this down with me. You can just watch if you want. Here in a second, we'll do this example, and you'll get a chance to kind of do this a little bit on your own. So if I look at this right here, this dy dx equals 3x squared minus 1, and I'm trying to find a solution to this. In other words, the equation that somebody differentiated to get that, right? Here would be my steps. This is a very prescribed process. First thing I need to do is I need to get all of the y's on one side and all of the x's on the other side. And do you see how on the left side there's a y and an x together, but on the right side is all x's? So in a case like this, what I would do is treat the dy dx like the fraction that it is and multiply both sides by dx, and that would give me dy equals 3x squared minus 1 dx. You will hear this repeatedly. I'll start off by saying it now. That step is extremely crucial because it goes to the heart of what an antiderivative does. An antiderivative undoes a differential, and so I need to get the variables separated. This is one of those steps that's really important. I call this a gateway step to getting any points at all on a question like this. You must show that you separated the variables. You must write it down and say, I've got all my y's on one side, I've got all my x's on the other side, and then we can proceed from here. But even if you proceed and you get a really nice answer, but you didn't show that step, we're going to have a problem. Okay? So please, please, please show the separation of variables. Once you've separated the variables, we want to remember how that we undo a differential is simply with one of those antiderivatives, right? The tall, skinny s. So I'm going to do the tall, skinny s to both sides. What is the antiderivative of dy? It's just a y. Yep. So it'd be y equals. And then what kind of a process would I use on the right side? Like what rule from that list of integration rules? It's power rule, just two power rules essentially. So wouldn't it be 3x cubed over 3 minus x plus c? The plus c needs to be there right there because we just did antiderivatives. The 3's cancel out. We end up with y equals x cubed minus x plus c. So that right there, my friends, that is the equation that someone previously differentiated to get that differential equation we had at the start. How could you check this? Do the derivative of that thing, right? If you do the derivative of that, you should get the original dy dx equals 3x squared minus 1. One other quick thought here. What kind of a solution is that? Do you think that that is a general solution or a particular solution? Why? The plus c is still in there, right? I would have to give you more information in order for you to be able to figure out what the c is. I'd have to tell you a point that is actually on the solution curve, and I didn't do that. So you really can't find the particular solution on this one. Here in just a second, you'll get that information. Zach, go ahead.
So would you need to show the intermediate step of having like 3x cubed over 3?
Nope, I'm totally okay if you cancel those out in your brain. So if on this, if all you did was you showed this step right here and this step right here, we're totally fine. The 3 over 3 thing, not too worried about. Good question. Okay, any others? Okay, fair enough. Let's take a look at our example down below. Example says, find the general solution and the particular solution of that differential equation. And then notice that I also gave you an initial condition. So with this one, we'll be able to find the C. So if you guys would, could you try to take this one right here and just find, for the moment, find the general solution? And then I'll try to catch up to you and we'll find the particular solution together. Fair enough? Okay, ready to go. Walking around, I saw a lot of good steps. I saw a lot of folks kind of moving forward too. So step number one is we need to get the y's on one side and the x's on the other side. So your first step might look something like this. Anybody have that?
Yeah.
Hey, Peyton, let's wind it up. So, I don't know. I'm hoping that on a quiz or test you'd be able to handle this no problem. But if that's all you wrote, you'd at least get a point. So that's kind of nice. Did anybody go ahead and write it like this? You really need to do that. We don't want to deal with fractional integrands because that's coming up next. We don't want to have to handle that, so we write that. Next step would be to find the antiderivative of both sides. That would give me y equals negative x to the negative 1 plus c, just using the power rule there. And that right there is our general solution. So I was hoping you could get to that. Walking around looking at folks' papers, it looks like the vast majority of you got there. Do you have any questions on that part right there? Okay, what follows next is a little bit new. It does say in this one we're supposed to find the particular solution as well with the initial condition y of 1 equals 0. What that notation right there means, that means when x is 1, y is 0. When x is 1, y is 0. So I'd plug in accordingly, y is 0 when x is 1. So the opposite of 1 to the negative 1 is just negative 1. And so c is equal to 1. So then you could write your final particular solution by writing y equals negative x to the negative 1 plus 1. So that right there, that would be your particular solution, whereas that right there was your general solution. Okay, how'd that go? Some of you guys I know went ahead and tried the particular solution. Did it go okay? As long as you interpret the y of 1 equals 0 part correctly, should go pretty well. All right, we good? You're going to get a chance to practice some particular solutions here again right now in the context of, yes, physics people.
Yes.
This is lovely.
Finally, I've been struggling for so long.
I've been waiting for this day.
Hope we can fix this. Here we go. So the first two we've done plenty with. The derivative of a position function is a velocity function. And the derivative of a velocity function is an acceleration function. That's right. And so knowing that we've done quite a bit with that, hopefully the reverse of this makes sense. If we did the integral of an acceleration function, we should get information about velocity. And if we do the integral of a velocity function, we should be getting information about position. It's just the reverse process, right? Make sense? So take a look at our example here. We got about 7 minutes, and I think we should be able to do this. Our example says a baseball is thrown upward from a height of 2 meters with an initial velocity of 10 meters per second. Determine the max height. Now, if you are in physics, you probably could piece this together with kinematics, right? But if you are unaware of the kinematics equations, we are decidedly short on information. Very short on information. I mean, think about what it's saying here. Determine the max height. Thinking back to chapter 3, if you're trying to find max height, don't you need an equation for height? And once you have that equation for height, wouldn't you set h prime equal to 0? Et cetera, et cetera. Now, we don't even have a height equation here, and so we don't even really have any idea where to start, but I will give you one piece of information to help us start. Once this ball is released, once somebody has thrown it, other than wind resistance, there is only one force acting on it. Gravity, yes. So gravity in meters per second squared is negative 9.8 meters per second squared. But gravity, what kind of a thing is gravity as far as kinematics goes? It's an acceleration. So I could say this, A equals negative 9.8. Ladies and gentlemen, this is where we're going to start. So I want you to think this through. Is an acceleration simply the derivative of velocity? So what I'm going to do is I'm going to rewrite the A. I'm going to respell A, and I'm going to spell it like this. dv dt equals negative 9.8. Does that make sense? I just spelled acceleration differently. It's still acceleration. So here we go. I'm going to try to find my velocity function because I need a velocity function, I need a position function, and I'm going to have to use calculus to get there. Here's what I do. I'm going to multiply both sides by dt to separate my variables, get my v's on one side and my t's on the other side. And to get to velocity now, what do I need to do? Yeah, find the integral, right? We're going to get rid of those differentials, so integrate both sides. This gives me velocity equals negative 9.8 t plus c. Now, I've got to figure out the c because I actually want to find the max height. So I need particular solutions, not general solutions. Anybody have any idea on what I could use to help me find the c? The velocity, yeah, what kind of velocity? And what does the word initial mean? When t is 0. Yeah, so when you see initial velocity of 10 meters per second, what that is really saying is that when t equals 0, v equals 10. That's what that initial condition really means. Initial vertical velocity of 10 means when t is 0, v is 10. So I'll use that. So say 10 equals negative 9.8 times 0 plus c. But if you're in physics and you know kinematics, you might see this starting to take shape. Are you seeing the kinematic for velocity starting to come into play here? So obviously negative 9.8 times 0 is just 0, so c equals 10, right? So you could say, all right, well, velocity equals negative 9.8 t plus 10. But remember, I'm trying to find maximum height. So what I'm going to do, again, is I'm going to respell velocity. Remember that velocity is the derivative of position, or the derivative of height. So I'm going to respell velocity like this. dh dt equals negative 9.8 t plus 10. Just respelled velocity. I know it's the derivative of height. You guys see the separating of the variables now? Just like we did before, I'm going to multiply both sides by dt. That gives me dh equals negative 9.8 t plus 10 dt. Look, I'm about to get height because if I take the dh and do what to it? Integrate it, I'll get height, right? I'm going to undo the differential there. So integral of both sides will give me height equals, and here's where a certain number that you might not have known where it came from shows up. What's 9.8 divided by 2? Negative 4.9. Those of you that have had physics, have you ever seen that number and thought, why on earth is gravity split in half? It's because to integrate t, you go t squared over 2. Maybe you didn't make that connection, or maybe you did. I don't know. Negative 4.9 t squared plus 10t plus c. How on earth am I supposed to find the c?
Plug in 2 and then plug in 0 for initial.
Yeah, from an initial height of 2 meters. That means when t is 0, h is 2. So 2 equals essentially 0 plus c. So obviously c is 2. So here is my height equation finally. This is going to finish in an interesting way. If, that's right, if you think about maximizing height, wouldn't we have to set h prime equal to 0? Don't we already have h prime though?
Yeah.
Isn't it back up there on this step?
Yeah.
H prime is v. Or you could look at it on the other step. I'll just do it right here. So you'd set this equal to 0. Now, a physics student is going to say, well, height is maximized when velocity is 0, right? But a calculus student is going to say, well, something is maximized at a critical number. Aren't we talking about the same thing?
Yeah.
And so you'd find the critical number of height by setting velocity equal to 0, also known as v prime or dh dt. And I don't know, you solve this, and don't you get like 1 point something?
1.02.
1.02 approximately. Now, as far as the justification goes, I think a second derivative test would be easiest. Why? You already have it. What is the second derivative? It's acceleration, and acceleration is always negative. And if the second derivative is negative, then any critical numbers will be where? At a maximum. Yeah, so you could do a second derivative test here and say that, yeah, okay, t equals 1.2, that's when the max happens. And then to actually find the height, wouldn't we have to take the t equals 1.02 and plug it in for t in the h function? So you could finally say h of 1.02 equals, and it's going to be roughly 7.102. Are you sure it's that? For sure you plugged it in? Okay. For those watching the video, we are trusting Peyton Case on this.
Creator of the awful joke.
That's true, that's true. All right, awesome. So I hope you guys made that good connection with physics, those of you that have had physics or are in physics. Make sure you watch the 4.2 video. Tomorrow we're going to talk about where this stuff comes from. See ya.